All right, this is a video of the problem that we did in class, and I added a sixth part. Remember I mentioned in class, what if you could lift the 1.5 pound mass with our spool system in 4 seconds? What would that mean the efficiency of the motor would be? So we'll work that as a sixth part. But since I didn't turn on the recorder in class, I thought, well, I'll just quickly go through the first 5 parts. When you go over this, remember, I forgot to give you that the efficiency of the gearbox is 0.3. Okay, so that part is actually part of the given. All right, so let's go over this. All right, so the first thing we did, I wanted you to be aware that gram centimeters is not a common unit for torque, but you can convert it to something that's common. You can convert it to SI where it's Newton meters. All right, so to do that, you realize that F equals MA, so mass in SI system is kilograms, times A, acceleration. The units for acceleration are meters per second squared. So the units for newtons is kilogram meters per second squared. Okay, so we start with the 100 gram centimeters. We multiply by gravity. Okay, and then it's just unit conversions from there. So we need grams converted to kilograms. Okay, so we go through that conversion factor, and then changing the highlighter. I now have meters, kilograms, seconds squared. So the stuff that's highlighted in orange is actually newtons. Okay, so I put that right here. All right, from here, I just need to convert this centimeter to meters. Okay, so I know that I have 100 centimeters in 1 meter. And at that point, this cancels. Okay, the grams cancel. I'm left with Newton meters. Okay, so it's 9.8 divided by 1,000 Newton meters. Okay, the data sheet that the motor came with had as a secondary axis, it had it drawn in with the units of millinewtons per meter. Okay, so milli is times 10 to the minus third. All right, and so if we put that in, we would need to multiply by 1,000 to not change anything. So that would cancel the 1,000, and we would get that this is 9.8 millinewtons meters. Okay, so that's part 1. Okay, part 2, the picture to have in mind is that you have the spool, and the spool has a certain diameter. We were given that the diameter is 3 centimeters, so that makes the radius 1.5 centimeters. And so the torque is the force operating down times the horizontal distance, the perpendicular distance. Okay, so we just take the 1.5 pounds, convert that into grams. The reason I do that is because I want my answer in gram centimeters. Okay, so 1.5 converted to grams, you have 453.8 grams in 1 pound mass. Okay, so that gives us this conversion factor. And then we multiply by the radius of the spool. Okay, so that gives us the answer for the torque at the spool. All right. Okay, so the next equation is involving gear ratios. Okay, so I said that you're gearing this down, so you need a gear ratio so that you'll be able to get the torque of the motor in the range that the motor can produce. Okay, the motor can only produce things between 0 and 120 gram centimeters. Okay, so it's geared with a ratio of 50 to 1, and so we take the spool torque, we divide by 50, and then because this is not a perfect gearbox, I need to also divide by the efficiency because I know the motor actually has to produce more torque to overcome the inefficiency of the gearbox. So I divide by 0.3, and that gives me the torque of the motor being 68 gram centimeters. All right. From there, given in the problem is a linear equation that talks about the relationship between speed and torque for the motor. Okay, this is different for different motors. Okay, you're seeing that when you look at your project and you see different motor specifications. Okay, so this is the equation for the motor we used in lab. Okay, so if I plug in the 68 into that equation, I get the speed of the motor. Okay, all right, so I do that calculation, I get 77,231.3, and this would be in RPMs. All right, so from there, we use the gear ratio, okay, to get the speed of the spool. Remember, it's geared down, right? So you take the speed of the motor and you divide by 50. All right, so the motor's spinning a lot faster. The gear on the spool shaft is a lot bigger, so it spins slower. All right, so that's why I need to divide by 50. Okay, and so you do that calculation and you get 144.6 RPM. All right, from there, I'm asking how long does it take to lift it? All right, so the way I get started on that one is I know I have to lift it through a distance of 0.7 meters. All right, so then I convert meters to centimeters. And then I know in one revolution, I know the size of my spool, the circumference of the spool will be 2 pi times r. All right, so that gives me the distance around one revolution of the spool. All right, and then I need to simply use the speed. Okay, so what I know is it's RPM, so in 1 minute I have 144.6 revolutions. So I put that on the bottom because that's the way the units line up. Okay, and if you convert this back into seconds, you multiply by 60 seconds in 1 minute, you get 3.1 seconds. All right, so that's what we went over in class, summed up real quickly. All right, so for this second part, let's change it up a little bit. Let's make the time that it takes to lift, all other conditions are the same except for the efficiency of the motor, of the gearbox. Okay, so we have the same gear ratio, all right, and the same mass that we're trying to lift. All right, so what we know is it takes 4 seconds to lift it. All right, so this is something we were able to measure in class. We could time how long it takes to lift the mass. All right, so that would let us estimate the gear efficiency, the gearbox efficiency. Okay, so I want a speed, and it's tricky to know how to get started on some of these, and so you just have to kind of think about it sometimes. But speed, what I could start with is I know that speed is a distance per unit time. So I know I have to cover 0.7 meters in 4 seconds. All right, so once I get that, I'm really good to go. It's just a unit conversion from there. All right, so I know that in 1 meter, I have 100 centimeters. And then I know that the distance for 1 revolution is 2 pi 1.5 centimeters in 1 revolution. Okay, I knew I was also working towards revolutions per minute. All right, so what I got right now is revolutions per second. Okay, so I know I have 60 seconds in 1 minute. So now I have, I'm going to put a subscript 2 here because this is the second condition, right? We're doing a different problem. So SP2 is different in part 6 than it would be for the other previous 5 parts. Okay, so when I do that calculation, I get 111.4 revolutions per minute. Okay, from there, I know that the motor spins faster than the spool. Okay, so the gear ratio is 50, so I take the spool under the second condition and get a second condition for the motor speed. Okay, so using the gear ratio, remember efficiency doesn't affect speed. The teeth interlock. It's As long as there's nothing slipping, that gear ratio equation is going to work as modeled. Okay, no efficiency needed. All right, so this calculation, we get 500 or 5,570.4 RPM for the second condition for the motor. All right, so from here, I can use the motor equation. And so the motor equation is, I get the speed, and that's equal to, I just plug it in. And what I'd like to know is the second motor torque condition. All right, so if I solve for tau m2, that would just be 5570.4 minus 16700. So I'm just solving this equation. And I get, if you use significant digits, I get 80 gram centimeters of torque. Okay. All right, so from there, I know that the torque required for the spool has not changed, right? I still have the 1 pound mass hanging off of it. So nothing has changed there. So I get 120.6 gram centimeters as the torque generated by the mass hanging from the spool. Okay? So, using the efficiency equation, I know that the torque at the motor would be the spool torque divided by the efficiency, divided by the gear ratio. All right, because I know, the motor torque's a lot less than the spool torque, and then I have to produce some extra torque to overcome the efficiency, so the efficiency goes on the bottom. Okay. All right, so I know that total is equal to 80. All right, so tau m2, we solved it from before, that's 80. We plug into these equations and you can solve for the efficiency of the motor. So, if we drop the efficiency, remember the first time we did it at 0.3. If we drop this a little bit, we get a slower lift time. All right, so think about this problem, think about different ways I could flip this around and ask you to solve for various things about this interesting setup that we learned from lab.